All right, 9-3, trigonometric functions of any angle. So this is getting into one of my favorite topics of mathematics, which is the unit circle. I'm so excited. But before we get started, there are some things you should probably note. I would definitely highlight this section where it's talking about the new, I wouldn't say new, the different way that we can look at the ratios. So in our previous sections, we reviewed that sine, cosine, tangent, we can describe the relationship of sine as being the opposite over the hypotenuse. But in this particular case, if we put it on a coordinate plane and we sort of imagine, if you will, a triangle coming down, let's say from this point, and we can make this right angle and have our x and y on the coordinate plane. And so we could say that our sine is going to be opposite, which is y, over hypotenuse, which is in this case radius, or r. And then our cosine would end up being our adjacent, which is x, over r, our radius. And then finally we can have our tangent is equivalent to our opposite over adjacent, which is y over x. So this is the same concepts that we've had before in geometry, but now we're just putting it on a coordinate plane. And when we put it on a coordinate plane, instead of thinking about it as opposite over adjacent, we can think about it as an x, y coordinate. And so that is a very useful method that we're going to use with our unit circle in a couple of seconds. So in example 1, it says evaluate the six trigonometric functions of theta. And part A of example 1.1 is written out in words, and the rest of them are pictures because that's how it's going to be presented in the homework. But I just wanted to show what it would look like if you didn't have a picture. How would the question be worded? So in part A, it says let -4, 3 be a point on the terminal side of an angle theta in standard position. So all I'm doing is I'm drawing my coordinate plane, and I'm going to put -4 and 3 as a point there, and I can draw a line connecting my point and my origin, or where my theta is, because remember we're in standard form. And from here I can create a right triangle. I just have to bring a dotted line down, put my little square that signifies a right triangle, and then since I know that I am on a coordinate plane and I have the measurements -4 and 3, I can actually include that on my triangle. So now that I have all this, I can use all of this. I can use the Pythagorean theorem or the piece that they gave me at the beginning, and I can plug it in and figure out, well, what is the radius of this? So we have used the square root of -4 squared. I'm going to put that in parentheses since it's negative, plus 3 squared. That'll give me 16 plus 9, which is 25, and the square root of 25 is 5. So now that I have that, I can go ahead and get started with my trig functions. Remember, we have our x and our y, our x value being -4, our y value being 3, and then our r value, or radius, being 5. So I'm just using that little piece that I had at the beginning. I'm just using that instead of my opposite over hypotenuse to fill out my trig functions. So sine would be 3 over 5, and cosine would be, or actually I can do the reciprocal first, 5/3. Cosine will be -4 over 5. Reciprocal would be -5 over 4. And then our tangent is going to be y over x, or 3 over -4, and the reciprocal is -4 over 3. All right, so now we can see that we have our trig functions. And so most of these are going to be like example 1.1. But example 1.2, it's just showing you, well, what do you have to do if you have to reduce? And so there is some extra work for this one. So let's get started. We have our x and our y value already given to us, so I'm just going to label that. I'm not going to draw anything else, and I'm going to figure out what my radius is. So r equals the square root of 3 squared plus -3 squared. Extend that, equals 9 plus 9, or 18, and that means that the square root of 18 can be reduced to this 3 times the square root of 2. You can keep it as the square root of 18, but in mathematics, especially if you're in honors, you need to be reducing or simplifying your radicals at all times. If you're in standard, you can probably get away with not doing it. when it comes to your next class. But if you have Miss Westcott, then she is adamant about reducing it correctly, so you should definitely learn it. So now that we have our x, our y, and our r, we can go ahead and figure out our 6 trig functions. So first one is negative 3 over 3 times the square root of 2. I can cancel out my 3's here, and that'll leave me with negative 1 over the square root of 2. Now, back in chapter 7 or 6, right around there, I taught you guys that if you have a radical in the denominator, that's no bueno. You have to multiply the bottom, the denominator, and the top, the numerator, by the radical, which in this case is the square root of 2. So if I do that, I should end up with, radical 2, I should end up with negative, because it's negative 1 times the square root of 2, negative square root of 2 over, and then the square root of 2 times the square root of 2 is actually 2. Really, it's the square root of 4, which equals 2. All right, so this has been, this is our trig function, and I put it in different colors so you could see that this is our final, or I guess you could say our final answer for sine. All right, now that we have that, we can go to our cosecant. So I circled the negative 1 over the square root of 2, because that was the answer I got originally, right? And if I take the reciprocal of this, because this all equals each other, just because we're simplifying it or we are rationalizing the denominator doesn't mean that it's a different answer. So I could have taken the blue, the negative square root of 2 over 2. I could have taken that, but it would have been extra work for me. So I'm just going to pick out of all of them the easiest looking one, which is the one with the number 1. So negative 1 over the square root of 2, and I'm going to rewrite it as the reciprocal, because that's what a cosecant is. So that's the square root of 2 over negative 1. And I can reduce that to negative square root of 2. All right, so all I'm doing, I'm just making sure I'm not doubling my work. I'm trying to avoid that. All right, so then I can do cosine. Cosine is the same idea, but now it's a positive 3. So really all our answers are going to be pretty much the same. It's just going to be positive. So I'm going to write it as a positive square root of 2 over 2. And that means when we take our reciprocal, our not cosecant, but our secant, we should end up with a positive 2 over 1 or a positive square root of 2. Tangent, again, is y over r. And so I can take this and do negative 3 over 3, which is going to reduce to negative 1. And so the reciprocal of that is 3 over negative 3, which is, again, negative 1. All right, so that is how you find your trig functions. Here is the unit circle. It's a special circle that has a center at 0, 0 and a radius of 1. So it's everything we've been talking about, but now we're just talking about when there is just a radius of 1. So in the previous examples, our radius could have been 5, it could have been 17, could have been 13, could have been 3 times square root of 2, whatever it was. But this is only for when the radius is 1. Because if the radius is 1, then the same numbers are going to occur over and over and over again, which is really cool. So the unit circle is very helpful in higher math, but for now, we're just going to sort of introduce it. So the first thing I need to tell you about the unit circle is that it can actually replace our ordered pairs. So if you think about it, if we take sine of theta and we say that it's equal to y over r, remember r is 1, so I put that over 1, and so anything over 1 is just itself, which is y. So I could say that whatever sine of theta is, that is going to be our y value, or in our ordered pair, it's going to be the y value. And the same thing happens with our cosine. Cosine is x over r, or x over 1, and therefore it equals x. So therefore, we could say x, y, the ordered pair x, y, can be rewritten as cosine, because that's x, and then sine theta. And parentheses. All right, and so that's really important, so please make sure you're highlighting that. That's extremely helpful later on. So this is our unit circle, and I've already filled in the pieces that we've already done. We've already done our degrees, and we've already done our radians. That was from 9-2 mostly. We sort of introduced it in 9.1, but mostly it's from 9.2. So we're done with that piece. Now we're adding on what the XY values are going to be, because if we know what the XY values are going to be, we don't have to compute it later on. We can just look at our unit circle and know what the answer is going to be. So the work behind it, I am going to show you the first two. The work behind it goes like this. So we want to find, let's say, cosine, or actually, before we get started, we know that since our radius is 1, the points on our axes are going to be very straightforward. At the x-axis on the right, it's going to be 1, 0. That means on the opposite side, it's going to be negative 1, 0. If we go to the y-axis, that's going to be 0, 1. And if we go down on the y-axis, it's going to be 0, negative 1. Okay, so that we can sort of establish at the beginning. All right, so now let's find those pieces, sort of those pieces of pi in between. So that's going to give me cosine of 30, and I'm going to draw my triangle. And in my triangle, I'm just going to put the pieces I know. I know my angle, I know that it has a radius of 1, and I know it's a right angle. And I can sort of, see that it's in the same shape as my what's on my unit circle. All right, so now that I'm done with that, I know that this is a special triangle, which is, again, something we've already reviewed over. So I can take that 30, 60, 90 triangle, and I can ask myself, well, what was the relationship of a 30, 60, 90 triangle? Well, across from the 30, it was an x. Across from the 60, it was x times the square root of 3. And then across from the 90, it was 2x. All right, and I know that my across from my 90-degree angle, that's my radius, and I know that equals to 1. So let me change the color, and let's figure out, well, what would x be if my radius is 1? So I would set that up equal as 1 is equal to 2x. I'm going to divide each side by 2, and I'm going to get x is going to equal to 1/2 because the 2's cancel out, right? So I know that my values, if I were to plug in that 1/2, there across from the 30 would be 1/2, and across from the 60 would be 1/2 of the square root of 3, or if I multiply across, it's going to be square root of 3 over 2. All right, so now I'm going to put those pieces on my triangle because I'm trying to visualize what's going on. So across from the 30 is 1/2, across from the 60 is going to be the square root of 3 over 2. So again, remember, cosine of 30, that's the same thing as opposite over adjacent over hypotenuse, or x over r. So if I look at my theta being at 30, my adjacent is the square root of 3 over 2 over my hypotenuse, which is 1. Well, anything over 1 is just itself, the square root of 3 over 2. So I know that my cosine, or my x value, when theta equals 30, is going to be the square root of 3 over 2. So I can fill that in to my ordered pair right here. I know that this cosine value at 30 is going to be the square root of 3 over 2. All right, and so if I were to do the same process again with my sine, or my y value, then I would get 1/2. All right, and so since 30 and 60 are so similar because they're the same triangle, the only thing that's going to happen once I go from my 30-degree angle to my 60-degree angle is these two values are going to switch. So now my cosine is going to be 1/2 instead of 3 times the square root of 2, and my sine is now going to switch and be the square root of 3 over 2. All right, so I'm just using the fact that a 30, 60, 90 triangle are related. I found the 30 pieces, and I just used that, all right, if I know they're related, and if I switch over to the 60-degree angle, the only thing that happens is my values switch. They don't change. I don't have like a 5 in here all of a sudden. They just switch because they are related. And you can think about, you switched corners, so therefore you should switch numbers, okay? All right, so what about 45 degrees? So let's say we have cosine of 45, and I'm doing cosine because I want the x value first. It's just how I wanted to do it. We could have done sine first, it really doesn't matter. But here's cosine, I'm drawing my triangle, here's my angles of 45 degrees, and my right triangle, and across from that is 1. All right, so 45, 45, 90 triangle. The relationship between a 45, 45, 90 triangle is the 45s are both x. That is the rule of the 16th postulate. And then across from the 90, it should be x times the square root of 2, which equals to 1. So I can do the same process again. 1 equals x times the square root of 2 this time. So now I need to divide each side by the square root of 2. All right, and those are going to cancel out, and I'm going to get 1 over the square root of 2, and if I rationalize this, I should get the square root of 2 over 2. And I'm sort of using information from my previous examples because I don't want to like repeat the same thing over and over again. We did 1 over the square root of 2 in example 1. I think it was 1.2a. So if you are confused on how to do that, go back and watch that example 1.2a to see the steps. But now that I have this, I can go ahead and plug it into sort of my x values if I want. So the first one is the square root of 2 over 2, and of course that means the second is the same. So now I'm going to put it on my sides, and since they're going to be the same, I'm just going to go ahead and include them on my unit circle. So the thing about this is that technically, if I wanted to think about it, the radius is the same every time. And as you can see, I'm sort of repeating my numbers. On this one little wedge, I have 2 1/2. And then on this wedge, I have 2 square root of 3 over 2s. And also, the 45-degree angle, I have 2 square root of 2 over square root of 2 over 2. So it would make sense that the next piece, since I'm sort of repeating my numbers, if you notice, it would make sense that in the next wedge, I'm going to have the same numbers. I'm going to be repeating those same numbers. But the only difference is that because I am now moving on my coordinate plane, I have the opportunity or the possibility of having negative numbers. When I move over into that second quadrant, my x values are negative and my y values stay positive. So I can transfer over these numbers and just make sure that I have my x values as negative. So it would be negative 1/2, negative square root of 2 over 2, negative 3 over 2. All right, and then when I go into my third quadrant, it's the same numbers again, but now both my x and my y values are negative. So this is negative square root of 3 over 2 and negative 1/2, negative square root of 2 over 2, comma, negative square root of 2 over 2, and then so on and so forth. All right, so now finally I get into my fourth quadrant, and I can, I know that my x values are positive, my y values are negative, so I'm going to put my negative with my y values here, and so it'd be negative square root of 2 in the y value, and then negative 1/2. And I'm going to erase the first couple because they're really, really thick and it's hard to read, so let me redo these. But these are the ordered pairs for a unit circle, and that's all that this whole thing is. And we could have spent a whole day on this, going over it. I used to spend one whole class period at Lee going over this because it's just a whole lot. But once you do it once and once you have this, it is extremely helpful, and you really don't have to do it again because you can memorize this. You don't have to worry about redoing it because these are going to be consistent no matter what. All right, so let's do example 2.1 and see how to use this very useful unit circle. All right, so here is example 2.1. It says use the unit circle to evaluate the 6 trig functions of theta. All right, and so the first two on the left-hand side are going to be sort of easier just because they are on our axis, or one of our axes. And so the first one is theta is equal to 180, and so we can draw our picture and put our line at 180 and just use the unit circle to figure out, well, what is x? Well, x is going to equal negative 1, and y is going to equal 0. R is always 1, and so we can do our sign, which is y over r, or 0 over 1, which equals 0. The reciprocal of that is going to have a 0 at the bottom, so we would put that as undefined. All right, cosine is x over r, or negative 1 over positive 1, which is negative 1. If you flip that, it's going to be the same answer, which is negative 1. Tangent is going to be y over x, which is going to be 0 over negative 1, which is 0. Do the reciprocal, and you get undefined again, because you cannot divide by a 0. Okay, so please make sure if you have a 0 in the denominator, your answer is undefined automatically. All right, letter B. This is pi over 2, so now we're looking at radians. It's the same thing as degrees. That's the same thing as 90 degrees. And so if we draw our line, it goes right here. X is going to equal to 0, and y is going to equal to 1. And I'm just double checking. X is equal to 0, y equals, yep, perfect. And then, of course, our radius is always equal to 1. So we could plug this in, 1 over 1 for sine. That'll give me 1. Same thing with cosecant. Cosine is going to be 0 over 1, which is 0. And if we flip this, this is now a 0 in the denominator, so it's undefined. And then tangent is going to be 1 over 0, which is undefined. Flip it, and now it's okay. 0 divided by 1 is 0. All right, so if it is on your axes, it's not super difficult. You just have to make sure you are plugging it into your ratios and your I guess, formulas correctly. All right, so what if it's not on the axes? And so that's what this is right here. We have example 2.2 A and B, where we have we have our terminal angle ending not on an axis. So 390, the easiest thing to do with this one after you draw your coordinate plane is to subtract 360, because this has one full rotation. And so that's all fine and dandy, but it would be nice to find a coterminal that made it a little bit easier to work with. So if we subtract 360, which is one rotation or going down a coterminal, we would end up with 30 degrees. So we can draw our line 30 degrees. One complete rotation at 30 degrees. Okay, so then if I want to label my x and y, my x is going to be equal to the square root of 3 over 2, and y is going to be equal to 1/2, both of them positive. Again, remember, r is positive 1, so I'm just not putting that because it's not super relevant right now. All right, sine is 1/2, because that is our y value, and therefore our cosecant is going to be 2. A cosine is going to be our x value, which is the square root of 3 over 2, and therefore the reciprocal would be 2 over the square root of 3. If I rationalize that, it's going to equal 2 times the square root of 3 over 3. All right. Again, I rationalize that by multiplying the denominator and the numerator by a square root of 3, whatever the radical is. Previously, it's been the square root of 2, but this time it's the square root of 3. So, and then the square root of 3 times square root of 3 is the square root of 9, which equals 3. That's how the denominator ends up without their radical. All right, so then we go to tangent. Tangent is going to be our y over x, or our sine over cosine. And so that's going to be 1/2. If I want 1/2 over the square root of 3 over 2. So when you have a complex fraction like this, you are supposed to rewrite it as like 1/2 divided by, with the division symbol, the square root of 3 over 2, and then you keep change flip. So you should end up with 1/2 times the reciprocal of the denominator, which is 2 over the square root of 3. Cross out your 2's, and you end up with 1 over the square root of 3. Rationalize that, just like we did with our secant theta, and you should end up with the square root of 3 over 3. All right, so then if I go to cotangent, I'm actually just going to write my answer as the square root of 3, because I'm taking this 1 over the square root of 3, and I'm just doing the reciprocal of that really quickly. Again, everything equals each other, so you're allowed to take any piece that would sort of make your work shorter and faster, and go from there. All right, same thing with 240. Or letter B, which is theta of 240. And so 240 is in the third quadrant, and it's normal. There is no full rotation or anything. Our x value, it should be negative 1/2, and our y value is negative 3, square root of 3 over 2. All right, so our sine is not difficult. Our sine is always just our y value. Therefore, our reciprocal is going to be negative 2 over the square root of 3. Rationalize that, and you should get 2 times the square root of 3 over 3. I do want to point out that these are pretty similar to what we had before. Notice how in example 2.2a, we sort of have the same calculations. So if you see that you're going to end up with the same calculations, you can just copy your answers down. Just make sure that your signs are correct, because in letter A, we were in quadrant 1 where everything was positive, but now we're in quadrant 3 where everything is negative, and so all of our answers are going to be negative now. So cosine is negative 1/2, therefore secant is negative 2. Tangent is going to be very similar to our previous tangent. If we do the work, we should end up with negative square root of 3, square root of 3 over 2 divided by negative 1/2. So if I were to rewrite it, it would be negative square root of 3 over 2 times negative 2 over 1. The 2's cancel out, and I end up with a positive square root of 3, because a negative times a negative, or really a negative divided by a negative, is a positive. So that is something interesting about this particular piece, and I'll go into it a little bit more in a second, but sometimes when you have all the negatives, you end up with some interesting, if you will, some interesting positive answers. So the cotangent of this would obviously be the reciprocal of this, which should be the square root of 3 over 3. Again, that computation came from the beginning of 2.2 part A, which I just did. I just didn't want to redo it again because I don't want to waste your time. So I wanted to talk about the signs really fast. When you're doing this, sometimes you are getting sort of used to the flow of doing the computations and finding the values and stuff. But you sometimes, common mistakes that I see are in the signs. And so like I see a lot of kids, they start getting used to doing these computations and they're doing great, but they keep messing up their signs, just little stuff here or there. So an easy way to sort of think about it, and I'll explain that at the end, but we could think about this as, in the first quadrant, everything's positive. So, our x values and our y values are positive. So when we, do our stuff, our signs, which is y, our y is positive. So that's going to be positive answers. And when we go to our cosine, that's going to be positive as well, those x values, so those are also positive. And then when you do the sine over cosine for tangent, that's positive over positive, so our answers are going to be positive. All right. And so when we go into our second quadrant, well, now our x values are actually, our y values are still positive, but our x values are negative. And so when we do our sine over cosine, our tangent is also negative. Moving on to the third quadrant, same sort of idea. Now everything's negative. So our y values and our x values are negative, but our tangent, remember tangent is sine over cosine, negative divided by negative is a positive, so our tangent is now positive. And finally, in our quadrant 3, we have the same sort of idea where our y values are negative, our x values are positive, and then sine over cosine, or positive over negative, or negative over positive really, is going to give us a negative. And so to sort of help us remember this pretty easily, you can think about when you're doing this, your values will be positive if you go in a circle. Okay, so starting with quadrant 1, ending with quadrant 4. If we go in a circle, our everything is going to be positive in the first quadrant. Circle that. Our signs are going to be positive in our second quadrant. Our tangents are going to be positive in the third quadrant. And then our cosines are going to be positive in the fourth quadrant. And so I taught this a couple of different ways, but one way that you can think about it as, or sort of remember it is with a mnemonic. You can say, all students take calculus, which not all students take calculus, but if you are, learning the trig functions, you're going to need it for calculus. So, there's that. So I teach this as all students take calculus, and that sort of helps people remember, okay, the order of sort of positive answers is, all of them are going to be positive, the signs are going to be positive, and the reciprocal of sine, which is cosecant. The tangents are going to be positive, then the cosines. So hopefully that can help you remember which values should be positive as you're doing this, and you're not making as many mistakes. All right, so reference angles. A reference angle is when theta is an angle in standard position. The reference angle would be the theta that is acute, or is the acute angle, theta prime, which is what that theta tick mark means, theta prime, formed by the terminal side of x and the x-axis. All right, so it's a weird sort of concept, It is a question that is typical for SATs, just to like a quick concept check to make sure you know what you're doing, what you're talking about. And so there's some pretty good ways to approach this. What I typically do is I write out, really what I think about is what do I need to do to complete or get back to the 180 line, that x-axis. That's really what I think about. The book likes to give you guys some formulas. So the formula is when you're in quadrant one, all right, your theta prime is going to be the same thing as your theta, okay? Because you're in the first quadrant, so it's all equal. How do you get back to the x-axis? Well, you go back the way you came, which is what theta is. And so sort of a picture to help you get an idea of that is, here's my acute angle, if you will, and I just put a light blue line showing you I'm going back the way I came to figure out what is the reference angle. It's a weird concept, I know. Just roll with me for a little bit. It'll get easier, I promise. So let's say we get in quadrant two. Quadrant two, same idea. All right, we're going to draw the picture. Here's my coordinate plane. There's my reference angle in the quadrant two. All right, to get back to the x-axis, this time instead of going back the way it came, I need to continue going or get closer to the 180 line. Okay, so I'm trying to get to the 180 line. That's all I really care about. And so I can think about this as one of two ways. I can either think about it asking myself, okay, well, what degree will get me there? Or you can use formulas, which is theta prime is going to be equal to 180 minus theta, or if you're working with radians, it's going to be pi minus your theta. All right, and I promise we're going to do examples in a second, but for now, let's go ahead and do quadrant three. Quadrant three is the same idea, but now we are drawing a coordinate plane and putting our reference angle in the third quadrant. And so we're pretty close to that 180 still, so this time I'm going to backtrack to get to that point, or you can use the formula theta prime is equal to theta minus 180, because we're just over the 180 mark, so we're just going to subtract 180 to get us back where we were. Or if you're working with radians, it'd be theta minus pi. Quadrant four, you should be very close to the 360 line, and so you should just move forward for this one, if you use the formulas, it's theta prime is equal to 360 minus theta, or if you're working with radians, 2 pi minus theta. All right, so let's do an example. Example 3.1, find the reference angle of theta, I should say theta, or find the reference angle theta prime. Okay, yeah, that makes sense. All right, so I'm going to draw the picture first. 210 is in my third quadrant here, and I'm in my third quadrant. I can ask myself, well, I can backtrack a little bit to get to 180. So if I want to think about it in that way, if I backtrack, I can say, well, I went over 180 by 30 degrees. Or I can use the formula from quadrant 2, which is theta prime is equal to 180, or in this case, 210 minus 180. Sorry, quadrant 3, my bad. All right, not quadrant 2, quadrant 3. All right, so that's the idea, all right? We're just asking ourselves, how much did we go over by, or how far do we have to go to get back to the 180 or 360 line? All right, so the negative 130, the easiest way to do this is to find the coterminal, so I'm going to actually, I never finished this problem, I'm sorry. So 210 minus 180 is 30 degrees. I finished it in my head. All right, so letter B, we are going backwards, 130. I'm just sort of guessing right now, but if I wanted to figure out its exact one, I can take 360 and subtract 130 to find the coterminal, and that should give me 230. If I want, I can think about it again as, how far did I go over? I was at 180 and I went over a little bit. Well, if I went over 180 by 50 degrees, or I can use the formula, theta prime is equal to 230 minus 180. 230 minus 80 is equal to 50 degrees. All right, so it doesn't really matter to me how you think about it. Typically, when you're in quadrant 3 like this, using the formula is very useful, but when you're in like quadrant 2 or quadrant quadrant 4, thinking about it in the way of, how much farther do I need to go is sometimes more helpful. Also, in letter B of 3.2, it's also helpful to think about it in the way of, how much farther do I have to go, because it's a fraction and it's radians. Degrees is not a huge deal because it's pretty easy, but degrees can get a little crazy, or radians can get a little crazy. So let's do some examples with radians. Letter A says 5 pi over 3. I'm going to go ahead and draw my coordinate plane, and 5 pi over 3 is in the 4th quadrant. Okay, so because I'm in the 4th quadrant, I can think about it one of two ways. I can ask myself, how much farther do I have to go to get to 360? Okay, think about it as I have 2 pies, I have 1 whole pie, and I have 2 extra pieces, 3 over 3 and then 2 over 3. 3 plus 2 is 5. Okay, how many pieces do I need to have to finish my circle or to get back to that starting point? Well, I am missing 1 piece, or 1 pi over 3. If that's confusing for you, then use the formula. The formula says theta prime is equal to 2 pi minus 5 pi over 3. We convert 2 pi to 6 pi over 3, subtract the 5 pi, and we get 6 minus 5, which is 1 pi over 3. That is our answer, okay? I don't care which way you think about it. If the formulas make more sense to you, then use the formulas. But if you are okay with thinking about it as what are you missing, or how much farther did you go by, then use that method. I'm just offering multiple methods for you to decide which one you like the best. All right, so example 3.2b, negative 7 pi over 9. Let me draw my coordinate plane. Again, I recommend using the coterminals for negative degrees. So that's what I did over in 3.1 over here. And so with the 230. So for letter B, I can go ahead and I can, figure out what is this going to be. This is going to be 2 pi minus 7 pi over 9. 2 pi can be converted to 18 pi over 9 minus 7 pi over 9. It's just going to equal 11 pi over 9. All right, so that's going to put me just over 1 radian, which is going to be in quadrant 3. Okay, so if I'm moving backwards, okay, think about it like this. If I'm moving backwards, okay, I have 7/9 of a pi, okay? If I want to complete the pi, I would have to get 2 more pieces, 2, because I have 9 minus 7, which is 2. So I need 2 pi over 9. That should be the answer. So let's just use the formula and double check our work. We're in quadrant 3, so I'm going to use my theta minus pi, which is, I'm using the 11 pi over 9 because that's my coterminal. All right, that can be rewritten as 9 pi over 9. 11 minus 9 is 2 pi over 9. Okay, so that is my answer. So we ended up with the same answer. Again, it doesn't matter to me which one you pick as long as you do that. The other examples that I have been skipping, just so you guys know, all the answers are on the teacher notes if you would like to work on them by yourself, and then refer to the answers on that I give to you from the answer key. All right, but for now, let's go ahead and just evaluate our trig functions. Okay, last example. Evaluate the following trig functions. And so we start off with sine of 150. This is actually on our unit circle, so we don't even have to do much work here. So we're going to use the unit circle. And if we go to the unit circle, we can see that our answer for sine, which is our y value, is 1/2. All right, letter B, cosine of 90, that's one of our common degrees. Again, use the unit circle. And cosine is our x value, which puts us at 0. All right, letter C, this one requires us drawing a picture, so I went ahead and drew my coordinate plane, and I'm going backwards so I can think about my coterminal. 360 minus 240 should equal 120. So I can sort of rewrite this as tangent of 120. And so I can take my sine, which is the square root of 3 over 2, and divide it by my cosine, which is negative 1/2. All right, so I'm going to just rewrite this. I'm going to change, flip, and the 2's cancel out, and I'm left with negative square root of 3. And that is my answer. Okay, so evaluating is, when we're using the unit circle, is very straightforward. It's not super difficult. But now we're just sort of going into what happens when you go backwards, or in example 4.2, what happens when you have secant and cosecant. So let's do one more pretty easy one, cosine of 7 pi over 4. That's on my unit circle, so my x value ends up being the square root of 2 over 2, and that's my answer. All right, so then we go to secant. Now, with secant, I can actually see that I have a full rotation. And I know I have a full rotation because if you take the denominator and multiply it by 2, that's going to equal 8. So anything more than 8 pi over 4 is a complete rotation. And so I'm going to go ahead and take 11 pi over 4. I'm going to subtract my rotation of 2 pi, which I can rewrite, as I said before, as 8 pi over 2. 11 over 4. 11 minus 8 is 3 pi over 4, and so I can rewrite this as secant of 3 pi over 4. Now, secant is the reciprocal of cosine, all right? So I can write this as 1 over cosine of 3 pi over 4, which is going to be 1 over the negative square root of 2 over 2, which equals negative 2 over the square root of 2, because anything 1 over anything, it basically just flips your whatever your denominator is. So in this case, I have a fraction, so I flipped my fraction. That's what I did. If I were to rationalize this, which is going to be negative square root of 2. That's our answer. All right, so just like in letter B, where I saw I had a full rotation, I am suspecting that C is similar in that aspect. So I just asked myself, okay, 6 times 2 is 12. Anything beyond 12 over 6 is a full rotation, and I have 17 over 6. So I know that I need to subtract 17 pi over 6, subtract 2 pi. That's one rotation. So I can rewrite that 2 pi as 12 pi over 6, and 17 minus 12, it gives me 5 pi over 6, so I can rewrite this as cosecant 5 pi over 6. Cosecant is the reciprocal of sine, so it would be 1 over sine 5 pi over 6, which if I use my unit circle gives me a value of 1/2. Again, when you have the reciprocal 1 over like this, your answer ends up being the reciprocal of your denominator. So my answer should be 2 over 1, which I can reduce to just 2. All right, so that is 9-3. It is a lot, I will admit, but it's not super difficult as long as you're using the unit circle and as long as you understand how to use the unit circle. So go ahead and give an attempt on your homework. You have two chances for each question. If you have any questions, please come to me during help class and I will gladly help you.